Vitamin B9, also known as folic acid, is most definitely the largest B vitamin so far. B1, B2, B3, B5, B6, B7 are all much smaller than vitamin B9. Now, to look at the structure of folic acid, you have a pteridine ring, and then you're going to have a benzamide, then you're going to have a glutamic acid or glutamate on the end. That ends up making quite a large chunky molecule, and the reason that it's folate or folic acid is the glutamate or glutamic acid has two carboxylic acid groups that can either be deprotonated or protonated, which ends up meaning that it's either folate or folic acid. Folic acid is normally the form found in supplements, but is actually the form that's not really found in nature all that often at all. Folate is normally the form found in nature. Now, inside of nature, folate is found in many green leafy vegetables and a lot of fruits. It's probably the first B vitamin that I've come across that isn't really commonly found inside of meats all that much. And so green leafy vegetables, spinaches, kales, asparaguses, all that sort of stuff is a very good source of vitamin B9. Then you're going to have quite vibrant exotic fruits like mangoes and papayas and bananas and all that sort of stuff. That is also a common source of vitamin B9. Now, an artificial source of vitamin B9, folic acid, would be inside of pregnancy supplements. You probably would have heard before that folic acid is very, very necessary for pregnant women to use for both themselves and for the baby. Otherwise, the baby will be probably quite deficient in the functions that vitamin B9 is used for. Now, vitamin B9 is used for 1 carbon unit transfers. So 1 carbon will be added onto this folate molecule, and there'll be loads of different stuff done to it, which I'll go over in a little bit. And then eventually that 1 carbon will be added onto another molecule. This biochemical process involves loads of different cycles. You've got the folate cycle, you've got purine cycles, you've got methionine cycles. It's absolutely massive biochemical processes. It takes a lot of time to wrap your head around, but for me, visual learning is the best way for me, and I found a couple of images on Google which really explained it quite nicely and weren't that hard to find at all. I didn't break my back having to try find a good explanation for this process, thankfully, and so hopefully I can explain these kind of images to you with relative ease. Now, this 1 carbon unit transfer can actually transfer many different functional groups in the end. At face value, the folate cycles and methionine cycles can only transfer an aldehyde and a methyl group. An aldehyde group is also commonly known as a formyl group, but that formyl group can then be dehydrogenated or it can be oxidized to form alcohols and carboxylic acids, which are very, very useful inside of the body. So essentially, this folate cycle and this molecule can transfer 1 carbon unit of aldehydes, methyl groups, alcohols, and carboxylic acids, which is a wide variety of stuff and is such a useful function to have in the body. This 1 carbon unit transfer is very, very useful for cell replication and DNA synthesis, hence why it's so necessary for a pregnant woman to take tablets of this chemical so often, because there is so much cell replication and DNA synthesis going on inside of the fetus in the womb. It's growing at a rapid rate and needs a lot of folate to actually keep itself going. Now, folate itself isn't really the active form of vitamin B9 yet. It has to go through a couple of enzymatic reactions. For instance, folate has to be turned into tetrahydrofolate, and this happens through 2 steps. Dihydrofolate reductase is the enzyme that does all this work, and essentially the pteridine ring on the folic acid molecule, or the folate molecule more rather, the right side ring, there's 2 nitrogens on the top and the bottom, and currently both are double bonded to a carbon and there are no hydrogens attached to it. These double bonds, when it turns into tetrahydrofolate, both of these break and then a hydrogen will be connected to the nitrogen, and then an extra hydrogen can also be connected to the carbons as well. That in total makes 4 hydrogens, hence why this molecule is called tetrahydrofolate. And tetrahydrofolate is basically where the folate cycles and methionine cycles actually start. And then once you have THF will enter the active site of the pyridoxal phosphate vitamin B6 dependent enzyme serine hydroxymethyltransferase. Now, what on earth does serine, one of the smallest amino acids, have anything to do with this large massive THF molecule? Now, THF will react with serine in the enzyme's active site, and serine will donate one of its carbons in the end after loads and loads of chemical stuff happens to the THF molecules and the serine molecules. The 5,10 methyl THF essentially ends up with an extra carbon, and you may have noticed the little amine group off of the pteridine ring. and there is one of the nitrogens on the top of the pteridine ring. These two nitrogens actually share a methyl group. It looked kind of weird, but it essentially creates another ring structure, which makes the molecule look entirely different to THF, but it's actually just got another carbon added onto it. And so this carbon has one bond to one of the nitrogens and one bond to the other nitrogen. There's not like two different methyl groups attached to both of the nitrogens, if that makes sense. And in the end, you also end up with a glycine molecule, which is the smallest amino acid with only 2 carbons, as well as water. And then 5,10 methylene THF will be turned into 5,10 methylene THF plus, but then 5,10 methylene THF is then turned into 10-formyl THF. Formyl is the common name for a 1 carbon unit of an aldehyde. Formaldehyde is the name for the chemical, which is a 1 carbon aldehyde. It can have another name like methanal, which is the more common IUPAC modern name. But inside of biochemistry, formyl just rolls off the tongue better than methanyl or methanal, I guess. So that's why it is used instead. Now, this 10-formyl group will then be turned into THF, which can restart the cycle, and formyl. That is the 1 carbon unit formyl, which can then be turned into either, it can keep itself, it can be turned into a carboxylic acid, or an alcohol, which is great. That is so useful for your body's functions. This formyl group can often be used for purine synthesis, purine being a particular type of ring inside of DNA nitrogenous base. Now, for the CH3 methyl transfer, this involves the methionine cycle. You're going to have THF, which I'm pretty sure will eventually turn into 5-methyl THF after being turned into 5,10-methyl THF. 5-methyl THF will give the 5-methyl, I suppose, to homocysteine, and that will then turn into methionine once it has had the methyl group added. This transfer actually involves another vitamin, vitamin B12, cobalamin, which is an even bigger molecule than vitamin B9, which is absolutely massive. It's insane. That is a cofactor for this methylation reaction to happen. But homocysteine and methionine are not really the only uses of this reaction. The methionine will then actually give its methyl group to a molecule known as SAM, and that will then be involved as a cofactor directly in a lot of other methylation reactors. SAM will turn into SAH, can't remember what those stand for the life of me. I think it's like sulfur, adenosine, something, but I'll probably type it up on screen anyway. And then because the SAM and the SAH has donated a methyl group off to something, that is a methylation reaction. Something has gained 1 carbon CH3 group, essentially, which is insane. That's a very, very long-winded way of adding a methyl group, I suppose. There are much quicker ways to do it in the real world instead of inside of the body. But I find that the process of adding carbons in the body, from a lot of research that I've done, is actually quite a difficult process. Taking away carbons is quite easy. Often you'll just decarboxylate them. And I suppose you can carboxylate things as well with biotin, which is a cofactor for carboxylation reactions, which I talked about in the previous video for vitamins and stuff like that. But adding a methyl group, CH3, is I suppose quite a hard thing to do when nothing on that methyl group is particularly reactive or special in a way. So it's quite a long-winded process, and this image that will be up on screen at many times in this video, I'm sure will explain it in a very good way if you are a visual learner as well. But with that, I recommend subscribing for more content like this, and have a good day.